things. But how transferable is this information? Do we have to, we certainly, I think, would have to do the same type of thing in mammals, like mice, and before we'd even get to humans. It seems like a few decades here that we're talking.
Right, and nobody says that this is the only anti-aging program
Okay.
that should. I'm 59. I don't feel like I'm as anxious for these technologies to come out as anybody. I want it to be now, but it's such a good shot, and basically it's pretty cheap compared to the cost of pharmaceutical research.
Okay.
For example, the kind of experiments that Rose advocates, and I wish him the best. I want to see that program go forward.
Okay. Yeah, someone.
I want to come back to. Here's a point I really want to make. It's not quite directly in line.
Go right ahead.
But the most credible, I think, damage theory of aging is about mitochondrial free radical. And that's Aubrey's theory. He really put it on the map and explained it in great detail. And that is that the oxidative process, a little background. I don't know whether this is necessary for all your listeners.
It's not necessary. No, it's not necessary for our viewers.
Mitochondria are the energy factories inside the cell.
Yes.
They get their energy by oxidizing sugars, and they turn that energy into electrochemical energy, which the cell can use.
Yep.
And in the process, they generate these free radicals, which are, they're like bulls in the china shop. They go around doing damage to all the active molecules. Now, the body's system for quenching these is the CoQ system.
Yep.
And I take CoQ10 as a supplement. I believed that damage done, that oxidative damage is real. But here's a piece of news that I just find boggling. I've been talking to Aubrey about this because I just learned of it 2 weeks ago. A study came out by Professor Hakimi at McGill University in Montreal.
Okay.
It turns out that the clock1 gene is a primary aging clock. It was the first aging clock discovered in worms, in C. elegans worms. I think it was 20 years ago that clock1 gene was first discovered in the lab of Johnson, if I remember right. So this clock1 gene, amazingly, has analogs in humans. And I think it's mind-boggling. The clock1 gene actually is a step in the synthesis of coenzyme Q. When you turn off the clock1 gene, you get less coenzyme Q. Of course, if you turn it off completely, you get no coenzyme Q, and you just die in the womb. You can't do without it. But what he's done, this Hakimi, is to genetically engineer mice that have one healthy copy of clock1 and one disabled copy. So they're producing half as much, and there's a bottleneck at the way to producing CoQ. And I had enough evidence in the damage theory that I thought, well, these animals are going to experience some more damage. Whatever you believe the ultimate cause of aging is, damage is certainly part of the mechanism that causes aging. So the mind-boggling result that comes out is that these animals with the clock1 gene, half disabled in one of their two copies, they live longer. They have lower rates of Huntington's disease, Alzheimer's, and Parkinson's disease than the control mice. And they have more oxidative stress coming out of the mitochondria. So I think this is a paradigm shifter. If we find out more about this and this turns out to be part of a major trend, it seems to me that it says quite clearly that the damage caused by these free oxygen, free radicals is incidental to aging. But it's not causative.
Okay.
One more piece that's much less technical. What can you do? What can you do right now that dramatically increases your production of free radicals? You can get out a jump rope. You can get out a jump rope and get yourself really hot and bothered, and panting, right? And then your production of free radicals goes way, way up. And what happens to your lifespan? What happens to the lifespan of animals and humans that exercise?
It increases.
It increases.
Yeah.
It increases. So there's another paradox. When you think about aging as a result of oxidative damage, you got to say that the things that are promoting oxidative damage in a big way actually cause us to live longer. That can only be seen as a hormetic effect. Hormesis is the effect I talked about at the very beginning hormesis is the biological effect where stressing you causes the body to overreact and extend the lifespan. Many kinds of stress, including exercise, extend the lifespan. But the body is programmed to overreact.
Yeah. Okay. I want to move on to a couple of points here. Some people had been discussing, some of the viewers here, and also it'll lead into a couple of other questions as well. So I'm thinking that the ways that you combat, say, aging is programmed, and what really has to happen here, if we do some experiments in mammals and flies and whatnot and find out these genetic pathways that we can tweak in order to extend aging or extend lifespan in humans, is basically it's going to be gene therapy, genetic therapy to change these genes, switch them on and off.
Well, you're getting way ahead. I'm not agreeing with that.
Oh, you're not going to agree with that? Okay, because that's what some people are.
Let me say. Let me give you an outline of what I see as the program. If you believe in programmed aging,
sure.
I think our program in the short term is hormesis.
Hormesis.
It's stressors, finding ways to stress the body and activate these life extension
built-in.
I exercise like crazy in my own life, and I keep my calories down.
And of course, you mentioned caloric restriction earlier. Yeah. Okay.
So hormesis is our key in the short run.
In the short run.
In the medium run, we're going to find chemicals that are that mimic the action of hormesis. For example, resveratrol seems to be acting as mimetic of caloric restriction. And I think we'll find other substances as well that you get the same gain without the pain.
Understood.
And I think that's our medium-term advance. And for the long term, I'd say that genetic engineering, it's you don't have to actually change the gene. You just have to shut them off. And biochemists know how to do this. You block the receptor. You find some molecule that fits into the receptor and yet doesn't do what the target molecule is supposed to do. This is a principle that's been used by pharmaceutical companies for decades. They're getting smarter and smarter about how to turn off specific enzymes in the body, like beta blockers, for an example.
Do we have to turn
SSRIs?
Do we have to turn some on as well as turning others off in order to prolong lifespan?
Well, the low-hanging fruit here is the aging genes that we can just turn off. Find the genes that are causing us to age more rapidly and just turn them off.
All right.
That's my long-term program.
Okay. All right. That's good. Thanks for that. Those 3 points there. At least splitting it out into short, medium, and long term. I got a question here from someone that asked prior to our show here. You've mentioned inhibiting apoptosis as a method of increasing longevity. Have there been any discoveries in the last couple of years to influence